Welcome back to our study of the Prolog language, which is an implementation of logic programming using horn clauses. And we have seen that the execution order of statements in Prolog is lexical, which means that whenever you ask for a query, in this case P for example, you could have asked for Q also directly, it does not matter. It will start scanning from the top, and wherever it finds the first P, it will see whether it can be satisfied. So, either that P would be a fact, which means there are no antecedents, or it may be a rule in which you go from P to the body of that rule and try to satisfy the rule, and in the body of the rule you go from left to right. So, we saw this example here, and we can visualize this as saying that to solve for P x y, you define this procedure structure. So, call Q of x, call R of y and call S of z in that order essentially. That will give you one answer. So, when you say call Q of x and call R of y and S of z, you will get the first answer, which is x equal to a, y is equal to 1 and z equal to c. Then if you keep repeating this, then you will see that the order in which the answers will be produced is as we saw recently. So, you can think of it as saying that for each solution of q x, for each solution of r y, for each solution of s z, the solution is x y z. So, we make this calls, nested calls, and generate each line of solutions. So, as you can see, there are 8 possible solutions here and they get generated essentially. We already said this, execute rules in the program order and goals in left to right order, expands the search tree in the depth first search order, and then it produces all solutions in the process. So, the same execution pattern can be seen as a search tree here. You started with this query of is P x y z true, and then we made a call to P x y z. We are renaming variables, because that is generally a good practice when you are visualizing what is happening in logic. Of course, internally Prolog will manage its own variable versions. So, you do not have to worry about that. But the way Prolog will see this as a depth first search is that it will first try to solve for the first variable, which is x 1, and the first option that it sees is that A is the q. So, it is looking for a q, then it is looking for an R with a variable y 1. It sees that 1 is an R, which is written as R 1, and then finally, it sees as C is an S. So, the leftmost branch in this tree gives you the first option. Then when you backtrack and come back here, it gives you the second option. Then you backtrack and come back here, it gives you the third option, where now y has become 2 essentially, y is 2 and z is c here, and so on. From there you will backtrack and come here, and then when you are done with this part of the tree, it will backtrack and go down the other branch and repeat the same process here. So, this is just to illustrate that what Prolog is doing is depth first search over this search tree essentially. We have mentioned this earlier, that such search trees can be seen as AND/OR trees. Why is that? Because you want to show that P is true, P of x y z is true, you have to show that Q of x is true and R of y is true and S of z is true. So, that comma is really an and in AND/OR trees, which we have been exposed to earlier, this is saying that to show that P x y is P x 1 y 1 z 1 is true, I must show 3 components and I must show all 3 of components. So, if you remember in AND OR trees, which are different from the tree that we just saw, which is sometimes called as an OR tree, there are AND nodes, which means you have to solve every branch below that essentially before you have a solution, and the solution, if you remember, is a subtree. So, we have this AND node, and then of course, we have the same query: is Q true for some x 1, is R true for some y 1, is Z true, S true for some Z 1, and then of course, there are these OR choices below that, that yes, Q is true for A and Q is also true for B, Q is true for R is true for 1, R is true for 2, and so on. The same process will be repeated here, and the same set of 8 solutions would be generated if you look at it as an AND OR tree. That is only a matter of perspective. So, terms in the language, we have defined the family of terms. Remember that we said that variables are terms, constants are also terms, that if T 1 and up to T n are terms, then if we have a function symbol, then the function symbol with those m arguments is a term essentially. We have seen that lists can also be terms, and which are kind of data structures that we can construct using that function called cons, if you remember. So, a cons pair and so on. So, cons has got a head and a tail, essentially it has got 2 arguments. Constant is a term, we have already said. We can say the function as a constant as a function with 0 arguments. That is just a matter of looking at things. Then we define numbers and strings, and they can be terms essentially. And some functions that we are interested in is this plus, minus, star and slash essentially. So, the examples of terms are given here on the right hand side. So, 1 plus 2 is a term, 2 star 3 plus 4 is a term, and so on. Terms are not evaluated, they are just stored as structures essentially, or data structures essentially. And Prolog and logic in general allows you to look at the structure of such terms. Numeric terms can be evaluated using the is predicate. That Prolog gives you that special thing, which says that you can evaluate a numeric term. So, here is an example. You can write x is 2 star 3 plus 4. 2 star 3 or 2 into 3 plus 4 is a term, but you can evaluate it using the is predicate. And Prolog would say the answer is yes essentially. It has an inbuilt notion of pi. If you say x is pi, it will give you the value of pi out for some number of some precision. You can say if x is sine of pi by 2, it will tell you that it is 1 essentially. So, when you say equal to in this, it is like saying that they can be unified essentially. In fact, this is what happens inside unification. You say x is substituted with 10. Here we are saying x equal to 2. Is used to evaluate numeric terms. If you want to compare terms, you have to use a different symbol, which is 2 equal signs with a colon in between. Anyway, those are language specific things. Hopefully, you would look at them. We have already seen lists. We said that lists are made up of these functions called dotted pairs, which sometimes we draw as a circle, which is also called as a cons pair, where we can write cons. Remember that cons is a term that we borrowed from Lisp as a language, but we can also use a head tail notation, which says that the left hand side is a head and the right hand side is a tail essentially. They are all similar notations and can be variously used effectively. We often denote lists with square brackets in Prolog, So, empty list is denoted by a pair of empty brackets. 1, 2, 3 is a list which is a same representation for all the diagrams that we have drawn on the right, but we can write it succinctly as 1, 2, 3. We can even write it as 1 is the head and the rest is the tail, and inside that 2 is the head and the rest is the tail, and inside that 3 is the head and the rest is the tail, and the rest is only an empty list essentially, which we can also write as cons 1, cons 2, cons 3 nil essentially. So, we have seen this before. This is the head tail notation with a vertical bar. So, if you say x y z vertical bar tail, that means x y z are the first 3 elements of the list, and whatever is specified in the tail is the rest of the list. So, this is the original notation where we use square brackets here. We have looked at unification in fair amount of detail. It is a process of making two expressions the same. The two expressions can be logical formulas, they can also be terms which have functions inside them, and in general the community uses the term functors. So, any functor, any two expressions with functors can be compared, and if there is a substitution which makes them equal, then unification algorithm will give you that substitution. So, here we are talking specifically about terms, but in general the Prolog at a high level also uses unification. When you give a goal predicate P, it will have to go looking for that P essentially, but of course, P will be a constant. Predicate names are not variables in first order logic. So, unification will be simple. A rule is selected for execution if its head unifies with the goal predicates, but we have already said that the name of the predicate is a constant, but the arguments to that may not be constant. So, unification may still work essentially, may still be required. Unification is the only mechanism for passing information between goal and the head and the body, and between body predicates essentially. So, you start with a goal, you match it with a rule with the head, and then whatever variables are there in the head, you will communicate them to the body and so on. It enables bidirectional information flow, passes input down the call chain and passes output up the call chain. So, our same program that we wrote earlier, defining the above relation. There are two facts, A is on B, B is on C, and there is a base rule which says that if x is on y, then x is above y, and the other rule is that to show that x is above y is that you must find some y, sorry, x is above z is to you must find some y such that x is on y and y is above z essentially. So, we have seen all this before, and given this program, now this in the shaded area here in this big box here, this is a logic program essentially. Even this program, if you ask this query, is above b y true where y is a variable, it will say yes, and if it is giving you all the answers, it will try to look for another answer and say that there is no other answer, and that is why it is saying false. So, here it is saying yes, and then it is not saying yes, it is giving you the binding which is in the most general unifier. Notice the semicolon, it says that okay, I have answered your query and I am giving you the next answer, and when it comes to giving you the next answer, it says that I can't find another answer. But if you ask for the query that is there something above C, then by our definition, and you can work this out, is that because B is on C, B is above C, and because A is on B and B is above C, A is also above C. So, it will give you two answers and then say there are no more answers. So, you must interpret this as saying that this is the first answer, This is the second answer, and this says no more. You can see the same process as to what is happening internally in logic. You start off with an empty most general unifier, and then you have this query above b y. It matches this rule above x 1 y 1 if something something something. It matches it by saying v is x 1. So, x 1 equal to v, and y and y 1 are same. So, y is equal to y 1. It reduces to a query which says that above b y 1 is true if b is on y 1. So, that is a sub goal in some sense, which is what is asked here, that is on b y 1 true. Then it finds in the program a fact which says that b is on c. So, it does this match here. It has already done this part, x 1 is equal to b and y is equal to y 1. Now, it does the third part which says that y 1 equal to c, and it finds that it has a solution. So, it gives you the solution that x 1 equal to b and y is equal to c. That your answer to the query, that is b above something, is true where y is equal to c essentially. Okay, so let us take another break, and we will come back and continue with how Prolog answers your queries, I think.